Welcome back to differential equations. In this video, I want to show you how to use the method of Laplace transforms to solve an initial value problem. As I mentioned in our introduction to Laplace transforms, the method I'm going to show you in this video is not the best way to solve this differential equation or this initial value problem. Specifically, I'm going to be looking at a second order non-homogeneous linear ordinary differential equation with constant coefficients. We already know how to solve a differential equation of this sort using the method of judicious guessing. And judicious guessing is definitely the better approach for this particular problem. But as I've said in the previous videos, I want to start by looking at problems we already know how to solve, making sure we know how to work with them, making sure we know how this process works. And then once we're comfortable with the process, then we can go on to some new types of things that we don't know how to solve already, that we don't know how to work with using the structure we've developed so far. Let me get my head out of the way and let's dive into a little bit of theory here. Let's assume that we have some function little f of t, which is differentiable. And let's name the Laplace transform of little f of t as capital F of s. All right, so we know we have a function, we know it is differentiable, and we know that its Laplace transform is defined. And with that, I want to evaluate the Laplace transform of f prime of t. Well, we know that this is, by definition, the integral from 0 to infinity of e to the minus st times our function f prime of t dt. And as we saw in the previous video, whenever we are looking at evaluating an integral for the Laplace transform, chances are very good that we're going to want to use integration by parts. This is a little bit of an odd one because we're going to set u as e to the minus st. We're actually using the exponential function as u. And that's because the other function is a derivative. If I set dv as f prime of t dt, then by inspection, what do you differentiate to get f prime of t dt? Well, that's the differential of f of t. So we choose f prime to be our dv because figuring out how to integrate a derivative of a function is really easy. And then du, well, that would be minus s times e to the minus st. I almost have room for the dt in there. So using our integration by parts formula, we're going to have u times v. So that's f of t times e to the minus st. We will evaluate that at 0 and at infinity, minus the integral of v du. So we've got a minus s, so let's minus a minus is plus s. We've got e to the minus st, we've got f of t, and we've got dt. Right, just moving the factors of du around in the way that's most convenient. Dealing with that first term is going to be a little bit messy, but before I even look at it, I want to point out this second term. That is exactly, from definition, the Laplace transform of f of t. So that's easy. That's something we can deal with right away. The first term, like I said, a little bit messier. We're going to have f of infinity e to the minus infinity. And assuming that f itself is not exponential, this is going to go to 0. Same thing we've used in the past. And then we'll have minus f of 0 e to the 0. Well, anything raised to the 0 power is not 0, is 1. So just rearranging these and writing them in the other order, we've got s times the Laplace transform of f of t, which is capital F of s, minus little f of 0. All right, there's another result that we should probably include in our table of Laplace transforms. Now let's continue one more. What if I want the Laplace transform of f double prime of t? Here I can employ a cute little trick. F double prime of t is the derivative of f prime of t. And so I can use the derivative formula that I just came up with to say that this must be s times the Laplace transform of f prime of t minus f prime of 0. And of course, we know that the Laplace transform of f prime of t is s times f of s minus f of 0. And if I distribute, I get s squared times big F of s minus s times f of 0 minus f prime of 0. There's another result that is probably worth having on your table of Laplace transforms. We could keep going. We could repeat this process to get the third, fourth, and so on derivatives of f. If we were solving third and fourth order differential equations, those would be very valuable. For the sake of convenience in this course, we stick to first and second order differential equations, so we don't have to worry about anything further, but it is something that we could do if we wanted to. So as an example, as I said at the beginning of this video, let's solve an initial value problem. Y double prime minus 3y prime plus 2y equals e to the minus 4t. This is a second order, linear, non-homogeneous ordinary differential equation with constant coefficients. And the driving function, e to the minus 4t, is a fairly simple exponential function. We know that we can use the method of judicious guessing in order to solve that differential equation. And we have a second order equation. We have two initial conditions, so we should be able to find a unique solution to the initial value problem. I invite you, after we're done with this, to go back and use the method of judicious guessing to solve this differential equation and confirm for yourself that you get the same result. But as I said, I want to use this to show you how the method of Laplace transforms works. And so the step of the Laplace transform is to say that if these two things are equal to each other, then the Laplace transforms of these two things should be equal to each other. Then I can use the property of linearity to rewrite the Laplace transform on the left-hand side as Laplace transforms of the individual pieces. Before going back and using the table of Laplace transforms to evaluate each of these things. The Laplace transform of y double prime in general is s squared times the Laplace transform of y minus s times y evaluated at 0 minus y prime evaluated at 0. The Laplace transform of y prime is s times the Laplace transform of y minus y evaluated at 0. I have no idea what the Laplace transform of y is, so nothing to do on that term. And then the Laplace transform of an exponential is 1 over s minus the coefficient. S minus -4 is s plus 4. Now, the reason that we cared about initial value problems. Looking at my initial conditions, I can fill in these values. Y of 0 is 1, y prime of 0 is 5. So I've got s squared times the Laplace transform on y minus 1 times s minus 5. Then I've got minus 3 times s times the Laplace transform on y. Minus a minus is plus 3 times y of 0, which is still 1. And then I've got 2 times the Laplace transform of y is equal to 1 over s plus 4. I'm going to keep all of my terms that include the Laplace transform of y on the left-hand side of the equation. The other terms I'm going to move to the other side of the equation. So I'll have plus s plus 5 and minus 3 all told is plus 2. And then a little bit more algebra. I can neaten things up on the left-hand side by factoring out the Laplace transform. On the right-hand side, I'm going to want to combine like terms, so I'm going to need some common denominator. Which is a lot more tedious than it is difficult, but distribute s squared plus 6s plus 8. Question why I have an equal sign there when I wanted to have a plus sign, but then add 1 to it and I get s squared plus 6s plus 9 all over s plus 4. And the left-hand side is s squared minus 3s plus 2 times the Laplace transform of y. I can get the Laplace transform of y by itself by dividing both sides of the equation by that polynomial. S squared plus 6s plus 9 all over s squared minus 3s plus 2 times s plus 4. So all that's left to do is figure out what function gives us this when we take the Laplace transform. Or in other words, y itself is the inverse Laplace transform of this fraction. S squared plus 6s plus 9 all over s squared minus 3s plus 2 times s plus 4. And thinking back to how we can solve these, you might just start to notice something from the previous video. It will become all the more apparent if I factor that quadratic in the denominator. It factors into s minus 2 times s minus 1. And yes, this is exactly the rational function whose inverse Laplace transform we figured out in the last video. Finding an inverse Laplace transform is tedious and time-consuming, especially when they get messy like this, and I don't want to do it if I can avoid it. So let's use the fact that we've already solved this to jump straight to the answer. Right? You can fill in all the details just by looking back at the previous video. This comes out to negative 16 over 5 times e to the t plus 25 over 6 times e to the 2t plus 1 over 30 times e to the negative 4t. All right, there we have it, I guess. I'm not going to say it's fun, but it works, and that's what's important. I would like you to see what you can do with this initial value problem. Here we have a first order linear non-homogeneous ordinary differential equation with constant coefficients. So the process should be a little bit easier than the last one, but I have y prime plus 3y equals 12 times the sine of 2t, along with the initial condition y of 0 equals 6. And I'd like you to take a couple of minutes, see where you can get to with that problem, and I'll see you in the next video.